So today we're delighted to have Masha Vlasenko talking on gamma functions, monodromy, and Apéry constants.
Thank you. Thank you very much for inviting me to speak here and for inviting me to the whole program. I find very interesting. I will speak about my recent work, joined with Spencer's work. But the most of today's talk will be introducing the context of this work, motivation, and this work is based on another work of Zagier and Golyshev. So mainly I will be speaking about work of Golyshev and Zagier today, and I will present our results with Spencer. I will be speaking about linear ordinary differential operators on the Riemanns here in P1 C without finite set of points. For such a differential operator, the important notion is the monodromy representation. And so if it's an operator of order R, it means the highest order of derivative is R, then near any regular point where coefficients do not have poles, the space of solutions to this differential equation is R-dimensional. It's a complex R-dimensional vector space. And then by doing analytic continuation of solutions, one can go around singularities, come back, and if you start with some function and come back, then it will be a different function, but still in the same R-dimensional vector space. And this is called monodromy of the linear differential equation, or it's a representation of the homotopy group based at the regular point where we're looking at the solutions. I will start with explaining a very old method of solving linear differential equations near a regular singular point. It's called Frobenius method. My goal in this talk is to introduce some numbers, starting from a differential equation, and we will see examples in which these numbers are interesting, some zeta values, multiple zeta values, and we will ask questions about these numbers, are they periods, for example. But the beginning is just the classical method of solving differential equations. We will be working over a field, a subfield of complex numbers, and we write the differential operator in the following form. Where theta is the derivation t d over dt, and the coefficients are rational functions with coefficients in this field. That's not the usual way to write linear differential equations.
You said. Oh, sorry.
So that's not the most usual way to write differential equations, but apparently using this derivation instead of d over dt is convenient for analyzing the singularity near t equals 0. I will be working locally near t equals 0 now. And it's also convenient for solving it, so for the Frobenius method that I'm going to explain. T equals 0 is a regular singularity or a regular point. We will write it like this, is at most a regular singularity. If and only if none of the coefficients in this form have a pole at t equals 0. So we assume it's a regular singularity, and we look for solutions in form which is t to the x, where x is a new variable we are going to vary, times a power series, which starts at degree 0. So I can rewrite it as the sum of this form, and we assume that a0 is 1. So up to rescaling, this doesn't change anything. So we assume that a0 is non-zero, and we are going to find x's which work, for which we have a solution of degree x, but they can be complex numbers in general. So to find such solutions, to find good x here, we rewrite the differential operator as follows. So we can expand the coefficients here in the Taylor series, in the power series of t equals 0, and then group the polynomials near powers of t. This way we are getting a presentation like this. Where pj are polynomials with coefficients in k of degree at most r. In particular, the important one for us will be p0, and it's given by this evaluation of the coefficients of the differential operator r at 0. This is called an indicial polynomial. Now we apply L to such a P. What we see is this: when theta derivation applies to t to some power n or n plus x, it's just multiplication by n plus x. That's why what we get is this. We want it to be 0 for phi to be a solution of L, but we can see that it's impossible, for example, when n equals 0, because these terms are 0, the previous n's are 0, so what we get at n equals 0 is just p0 of x, so it's sort of impossible to solve it clearly unless p0 of x vanishes. But what we can do, we consider this as a recurrence relation, which determines the sequence of an's starting from a0 being 1. So what I mean is a0 is 1, a1 is minus p1 of x minus 1 over p0 of x, and so on. So this recurrence determines the sequence of rational functions with coefficients in k. Such that this is 0 for n greater or equal to 1. And so the result is this. If we write a of x t, the sum a n of x e to the x plus n, then L p is p0 of x t to the x. L acts in the variable t. So the first thing to do is to take x to be a root of this indicial polynomial. The roots are called local exponents. That's already a solution. So just substitute the root here, we are getting a solution. But we can also differentiate this equality in x as many times as is the multiplicity of the root. And this way we're having more solutions. But so let me write it here if alpha is a solution to the initial equation of multiplicity m, that gives us m solutions, and they are given by the formula formula gives us log t, and we differentiate t to the n plus x in x, but it's log t times what was called t0 plus the sum a n prime, the first derivative in x, and so on, up to t m minus 1. So the only problem here is that these are rational functions. We should worry if we can evaluate them, if alpha is not the pole. The denominator of these functions, a n of x, can be seen from the recurrence. The denominator is, sorry, I think it was mistaken. So to put a1 here, we would have x plus 1 and p1 of x. Sorry, this is a1. So a1 has p0 of x plus 1 in the denominator. a2 has p0 of x plus 2 in the denominator, and so on. So if alpha is a root of p0 such that alpha plus 1, alpha plus 2, and so on, alpha plus positive integers are not roots, then indeed we are getting solutions here. And otherwise, this method would need some correction. I will not discuss this. There is a way to deal with such a case. But so let me summarize it here. So, the differential equation has order r. The initial polynomial p0 of x is of degree r. If p0 of x has no roots that differ in integer, we are getting a basis in the space of solutions of L, and it's called the Frobenius basis. So let me write an example of such a case. The thing that you can see in this simple construction from a recurrence, that if we started with a differential operator where the coefficients only involve constants from field K, then all the power series in this Frobenius basis will be with coefficients in the field K. That makes them interesting for elementary number theory. So we produce some series from a differential operator and we can look at their coefficients. Example. We will look at the hypergeometric differential operator of order 2 with parameters 1/2, 1/2, 1. If I write it using the derivation theta, it looks like this. So the solutions look like this. The Frobenius basis. Where this is the co-color symbol. What is written here is denoted. This is the hypergeometric function with the parameters 1/2, 1/2, and 1. But if you try to solve it in power series, there is no other power series solution, but there is this second solution in the Frobenius basis because the initial polynomial here is x squared. And the second solution is like this. These are some rational coefficients. Maybe everyone have seen hypergeometric functions, but these log solutions to hypergeometric differential equations are more sophisticated. But they are produced by the Frobenius method. And now the remark which makes the Frobenius basis interesting in geometry. If N is a geometric differential operator, that means that it's of Picard-Fuchs type, or it's coming from a Gaussian connection. Then, under some assumptions, the Frobenius basis spans the Durand structure of the limiting force structure at t equals 0. What does it mean? Assume that it comes from a family which is defined over the field K. We can extend the field K at this point. Then this will be the K span of the functions in the Frobenius basis, the Durand structure, the limiting force structure. And that means that well, a geometric differential operator has special solutions which are period functions, period integrals, and they form a Q structure in the space of solutions. And if we express them in the Frobenius basis, if we express such period functions in the Frobenius basis, then the coefficients will be periods of this limiting force structure. Example, so I will just continue this example with this, it appears to be geometric, this differential operator. Here are some examples of solutions which are period functions. So it's an exercise to check that this elliptic integral satisfies the solution of this differential equation L. That, for example, can be checked by expanding the root under the integral as a power series in T and integrating term by term. And what we find is the result is pi times the hypergeometric function, pi times the first function in the Frobenius basis when T is close to 0. Let me do another elliptic integral, which is also a solution to this differential equation. That is equal to the numbers we see here are periods of the limiting force structure of the Legendre family of elliptic curves. That's the family which gives this Picard-Fuchs differential operator for its first mode. this and the section on
So what do
solving
you,
differential.
what do you mean by, so can you read the filtration, Hodge filtration on the solution of your
Yes,
problem?
you can write. So the Hodge filtration, the limiting Hodge filtration, will be spanned by the Frobenius basis. So it will be like phi0, then phi0, phi1, phi0, phi1, phi2. This is the limiting Hodge filtration. But all is done here under. I mean, it's a bit more complicated. So we can say this in the case when we have maximally unipotent monodromy, then the Hodge filtration is so simple. Otherwise, one needs some combinatorics to explain it. But it will be in terms of this Frobenius basis. Okay. So now I changed the topic. I will speak about the proof of irrationality of zeta of 3. At first glance, it's something else, but we will come back to this topic of differential equations soon. Let me say a word about this Frobenius basis and limiting for structure before I start the next part. So imagine that you are in some regular point and you connected by two paths to two different singularities. Then there is a Frobenius basis in the space of solutions near this point for each of the two singularities. You just bring them back along these two paths. So you can express one basis through another one. Like if you were doing periods, you have two different case structures in the space of solutions. But these numbers, this is called sometimes a connecting matrix or transition matrix. But these numbers are not that much investigated. They seem to be numbers that connect two limiting Hodge structures. So in my talk, I will be speaking about a particular situation of this, when we have some restrictions on the local monodromies. You will see which restrictions. But in general, it's some problem which is at the initial stage. So, part 2. In 1978, Roger Apéry proved that zeta of 3 is irrational. Let me remind you the proof. So it goes like this. He considers a recurrence where P of n is a particular polynomial. And there is a solution of this recurrence by an integral sequence starting with a0 is 0 and in general a(n). This is an integer solution of recurrence. And then he considers another solution to the same recurrence with different initial conditions. B0 is 0, B1 is 6, and then just run the recurrence because two terms is enough to determine the rest. Same recurrence, but we are getting denominators. This is an integer sequence satisfying it, but here they will be rational numbers. So Apéry studies them. He says that and Q Bn is an integer, so there is some control of denominators, where Bn is the least common multiple of numbers from 1 to n. And these two sequences approximate the zeta of 3 as follows. over an tends to zeta of 3 as n tends to infinity. But this is a very strong property that Apéry proves by some ingenious arguments. It was not clear what it means and how that could be used to do more irrationality proofs, and so far there are no more irrationality proofs of that kind. But to finish the argument, to show that zeta of 3 is irrational, just note that by prime number theorem, Dn, the least common multiple of numbers from 1 to n, behaves like e to the n asymptotically, where e is the base of the natural logarithm. So it follows that dn cubed times cn, and just multiply this by dn cubed to make both sequences integer. It tends to 0 as n tends to infinity, because e cubed times c is less than 1. So with this, assume that zeta of 3 is a rational number. Then here, and we multiply it by dn cubed to have this integral and this integral. So then all these numbers become integers with a fixed denominator. And such a sequence can't tend to 0 unless some terms are 0. This is the proof. So after Apéry presented this proof, there was a lot of, there were many attempts to understand it in different ways. Let me explain what perhaps Boykers invented. Another interpretation of this proof. So a recurrence corresponds to a differential operator, as we have seen when we did the Frobenius method. We basically deformed a recurrence. So in Apéry's proof, the differential operator would be this one. It's a differential operator of order 3, and the Fourier series, the generating function of that sequence an, is the first solution in the Frobenius basis. Just the operator transforms to the recurrence. It's a solution to that. Consider the generating function of the second sequence. Apparently it's not a solution, but it's a solution of a non-homogeneous differential equation. It's the number 6 here, because it doesn't solve the recurrence with n equals 0 somehow. So to pass to Apéry's proof to explain why zeta of 3 appears here, we notice that t equals c, c is the number here, is a singular point. So if we rewrite this, we will see that the coefficient near the highest order of theta is this. So the two roots of these quadratic polynomials are c, that constant written here, and 1 over c. So this differential operator has singularities at points 0, infinity, c, and 1 over c, 4 singularities. And we are talking about the closest singularity to 0, the small number c here. This singularity is a reflection point. A reflection point means it's a regular singularity, where local monodromy is pseudo-reflection. So local monodromy means that this is point C. We are working near some regular point of our choice. We are considering solutions here. We do a loop around C. Let me call it sigma C. Analytic continuation along that loop is a linear operator in the space of solutions. And pseudo-reflection means that the image of the variation of this map, so the variation of this map minus identity, is one-dimensional. So whenever we go around a reflection point, what happens with the solutions, they add a multiple of one chosen solution. This is called a reflection point. For example, all hypergeometric differential operators of all orders have a reflection point at t equals 1. So this reflection point, let me write a lemma. If C, which is not 0 or infinity, is a reflection point for a differential operator L, then it stays a reflection point for the operator theta L, higher order. Why theta L? Because this is a solution with the right hand side a constant, so theta L will kill phi. This is an operator of order 4, one's bigger, which includes both phi 0 and phi as its solutions. Therefore, since this is a reflection point for theta L, there exists a constant kappa such that phi of t minus kappa phi 0 of t is sigma c invariant. To conclude that, one needs to know that phi 0 is not sigma c invariant. Therefore, like if you have any two solutions which are not sigma 0 invariant, then you can make a linear combination which is sigma c invariant because of this condition. It's a linear algebra. Okay, and this kappa appears to be zeta of 3. That is an interpretation of Apéry's, not proof. This is not the entire proof, but at least it's the setting in terms of differential operator that was presented by workers. And then one needs to explain the integrality properties of the two sequences, which is a separate topic. Okay, so such things like kappa here are called Apéry constants of differential operators. And next I'm going to define them in a general setting and have some theory about these numbers.
So what happens if not equal to 6?
Say it again, please.
If not equal to 6, replaced by other numbers, what happens?
If what is replaced?
Alpha equals 6, this is condition, right?
Ah, okay.
Not
Well,
6.
6. What do you mean? What happens?
If not 6, could you create other numbers?
Well, I can. You see, if there was a different function, a non-homogeneous differential equation with some right-hand side instead of 6, right? I could invent a differential operator which kills that function anyway. So some extension. I can multiply L by an operator which kills that function. But I will not always have this nice property as in the lemma. But if you want to deal with this situation, you can try it. Maybe it's a reflection point and maybe this constant is defined. But just wait a second, we will do more general stuff. I'm just finished with the Apéry proof here, and now let's think about differential operators. constants. I return to this setting of the differential operator of order R. And I will assume that all coefficients vanish at 0. That condition transfers into local monodromy amount 0 being unipotent with one Jordan block. But just let's consider differential operators with this assumption. It's an assumption on their local monodromy. The Apéry operator satisfies this assumption. So consider the Frobenius basis for under this assumption. It's given by, I will rewrite the formulas we had at the beginning of this talk more concretely in this situation. These are certain power series, I denoted them Phi1, because they are analytic at t equals 0, and they are given by the following formula. This is A(n) of x is the deformed recurrence in the Frobenius method. So the coefficients of the phi k on are k's derivatives evaluated at 0 of this deformed recurrence in the Frobenius method. They are power series with coefficients in field k. Now we note that these functions are also defined. So far, for the Frobenius method, k is from 0 to r minus 1. We have r functions, and this is the basis in the space of solutions of the differential operator. But these functions are also defined for k greater or equal r. We can just continue differentiating the recurrence in the Frobenius method. So what is this? If we just take these higher Frobenius functions, what are they? They come from the Frobenius method as follows. So we have the series phi of xt. So if we expand A(n) of x as a Taylor series in x and group coefficient near the powers of x, we can write it as follows. Or we can do to pass from here to here, we have to write t to the x as exponent of x times log t and expand it in the power series. So the logs will represent here. And so these functions in the Frobenius method, they are just coefficients of the phi in the Frobenius method as power series in x. So what we remember that in the Frobenius method, space satisfies what is now looks like this. So the initial polynomial is x, so x to the power r. Just evaluate this at 0, and due to this condition, it's x to the power r. So we see that the functions phi k, and k is bigger than r, satisfy the differential equation with the right-hand side, which is log t, k minus r, over k minus r factorial, or k greater or them higher Frobenius function. That name was given by Zagier and Golyshev. In particular, from this formula, we see that they satisfy differential equation theta k minus r plus 1 times L. This is the differential operator which gives them. Okay. So I needed to be so precise about this Frobenius method to convince you that if L has a reflection point at some point C, then all these theta to higher power times L will have a reflection point at that C by the lemma here. You can just repeat the lemma. Multiplication by theta doesn't change the reflection point property. And now we can apply it to all higher Frobenius functions and get sort of the next step in this Apéry proof. More numbers, not just zeta of 3. So Golyshev and Zagier computed them, and let me show you the result. So first I will define them precisely. Assume L has a reflection point at T equals. Choose a solution of L that spans the image of sigma C minus identity. That's a reflection point, and this is a one-dimensional image. This is a special solution such that when you go around C, all solutions add a multiple of this. And then we can define Apéry constants. Kappa 0, kappa 1. Just a second. Yes?
Possible. My memory for the paper of Golyshev is you have the first, in this case, 2 Frobenius loops, 3 Frobenius loops that solve the equation. But the next one, from the modular point of view, was the original times some Eisenstein series, was not the same as Apéry's.
They are different. I can tell you why.
No, but now you've
Just a
written the
second.
same equation
No.
because L5
No, you
is
have to
constant.
divide that L by the leading coefficient by 1 minus 34t plus t.
No, but not just what the
No,
constant.
I will explain you. That's slightly different. Just let me finish this so people don't.
But now you
waste
seem
time.
to be saying it's the same because
No, they are
your
not the same.
phi
That L
Apéry.
is not the L in the Apéry proof is not written in the shape as I'm writing it here. It's L times a
Oh, I see,
rational
that's
function,
right, okay.
and that rational
Thank you,
function
thank you,
changes
okay.
everything.
It changed everything. Yeah, thank you.
So we define Apéry constants as follows: sigma C minus identity applied to the Frobenius basis at 0 is kappa k times delta. So this is a function, this is a function, and this is a constant. Just by the reflection point idea. Okay. So these are numbers which come from the monodromy of this differential operator. They are defined up to rescaling. So if I change this delta t by a constant times delta t, then they will all multiply by the same constant. But what makes sense is the whole vector, like in infinitely many numbers. We can rescale them, but still we think it has the whole. And let me show you how that works in the Apéry example. So Golyshev and Zagier do L equals what was on board. As in Apéry group, exactly that differential operator, and they discovered that the values are as follows. Let me rewrite this as 2 times zeta of 2. Now, kappa of 3 is the first higher Apéry constant. It comes not from a solution of L, but a solution of theta L, the first higher Frobenius function. It's 17 over 6 zeta of 3. And kappa of 4 is pi squared, pi to the 4 over 45, which can be written as 4 over 5 zeta of 2 squared, or 2 times zeta of 4. We do one more. Kappa of 5 is 7 over 5 zeta 5 minus 17 over 3 zeta of 2 times zeta of 3. I mean, in this program, people should spot that these are Q linear combinations of products of zeta values which are weighted. So kappa of 2 is of weight 2. Kappa of 5 is of weight 5. Here it's 5, 3 plus 2, and so on. And this is an amazing discovery of Don and Vasily. Moreover, they did them until kappa 11, but numerically. So they computed kappa of 3 in the paper on the gamma conjecture in mirror symmetry, that kappa of 3 proves the gamma conjecture in some case, and the rest they computed numerically.
So,
And they,
I think from the Don's lecture, I think the L is geometric, right? Is L is geometric?
what was geometric? Oh, yes,
Of
it
course,
is geometric.
of course.
It
Right,
is, it's a
it's the same.
Picard-Fuchs operator of a family of case-free surfaces.
Yeah.
Yes, yes, yes. That's a Picard-Fuchs operator.
That's important, right?
Yes.
I think it is.
It is important. To prove that this is zeta of 3, we would do some geometry, or
Is it
modular
related
forms,
to-
which is also geometry.
To make Maxwell structure?
No, we won't. I mean, the current methods of computation do not use the mixed force structure, but we would use, for example, a modular parametrization of this differential operator, and then use Einstein's series to show that this is zeta of 3. But they have different methods. I think Tom had a lecture last week where he presented different methods of computing of kappa of 3, and the rest is numeric. Okay?
Well, also one very small comment. I mean, we noticed this, I don't know the meaning, I wonder if you do. Kappa 5 contains 17/3 zeta of 2 zeta 3. That's exactly kappa 2 times kappa 3. Right? It's not a coincidence. Minus 2 times 76, zeta 2 zeta 3. So if you take somehow, what we did is we took the log of the generating function, and that was much simpler. So that term, I think, goes away.
Yes,
Or,
yes,
I'm not
yes,
sure,
yes.
I have no idea why that's true. Do you
Yeah,
know why?
I have some ideas, but there is nothing
Nothing clear.
finished. So
Okay.
let me continue
Yeah,
the
but it's
lecture.
usually
So
small.
this is
Kappa
the
6
most
is-
interesting point in my lecture. This data. Yes,
What will be kappa 6 then? I'm getting curious.
kappa 6. I don't remember, but it's again the story continues. Some rational linear combinations, which you can find in the paper of
Yeah,
Dr.
we gave the table.
Yes.
But the problem is,
Let me write
kappa
how-
5 is kind of canonical, but even kappa 4 is in zeta 2 squared, is in zeta 4. You get to kappa 6, it's in zeta 2 cubed, zeta 2, zeta 4, is zeta 6. So of course it's multiplied to 6, but you don't know. Sorry, it's the zeta 3
Okay,
squared.
just let me mention Don's discovery that kappa 11 is the first one that involves a multiple zeta value. So it's more interesting than zeta products. That's it. Okay, so let me now talk about these numbers.
Well,
bit.
every equation here after the third should have a question mark.
Yes, yes, this is question mark,
It's all-
numerical data, but so we trust that this is so, it's a conjecture. So the first three that come from this differential operator, which is of Picard-Fuchs type, they are periods of the approximately some combinations of them. They are related to periods of the limiting mixed-Hodge structure to the phenomenon of pastry surfaces at zero. But when we go to higher kappa constants, higher Apéry constants, they are what we see in this picture. They are solutions to some extensions of this connection. And here it can happen that theta j l, it not can happen, it's just that these differential operators may not be geometric. There is no reason to expect it to be geometric. So that's a surprise that we see some periods here.
But how to prove that it's not geometric? I mean, why you say that? I mean,
Yeah.
it's not geometric.
Yeah, there's an ambiguity in the language that you don't mean that we know that it may not be. that
It
isn't.
may not be, right?
As a,
It can happen that for some L, this
That's
is
correct.
geometric.
It may not be geometric.
Yes, but
yeah, but we don't know it may not be.
yes, this is not a theorem. It's just that we have no
Well,
reason.
anything that may happen, may happen.
Yes, but
If
that's
you don't,
not a
then
big
you-
problem either, because you could imagine that you can cook up some smaller geometric differential operator for which they are still solutions. It's just that at first glance, this is a surprise, and we don't know the exact answer, why we see periods here. This is the problem I'm going to speak about in the rest of this talk. So let me write the problem. I have 6 minutes left, not much. So I will not write it down. I will just say that the problem is to show that the Apéry constants of Picard-Fuchs differential operators are periods. And secondly, if we show, give some motivic construction for that. Say periods of what are they? And here is the first step in answering this problem. This
But
is
what is the problem say? Whether it's geometric or whether you interpret the
the
theory?
problem. I have 6 minutes, but okay. The problem
So the numbers
are
themselves are
Apéry constants
Oh, simply that. I'll take it.
of Picard-Fuchs differential operators. Periods. And then you can answer at different levels. You can just compute, prove these formulas and say they are periods, but in general, give a motivic construction. So we prove that the generating function of Apéry constants is the following. R is the order of the differential operator in this story.
This for any Picard-Fuchs.
No, for any L. For any differential operator,
Oh.
which satisfies my assumptions in this section, maximally unipotent monodromy near zero, and a reflection point. So just this construction. So let me explain this formula. M here is the minimal j such that kappa j is non-zero, the order of the generating function of the Apéry constants. And this here is a Mellin transform of a solution to the adjoint differential equation. The adjoint, well, there is a formula to define it, but it corresponds to the dual connection. There is duality on connections. And to write it in formula, you just do this. Substitute minus theta and interchange theta and t from left to right. That's a solution to this equation. There is some solution. And here, sigma is a loop. A loop such that both psi and t to the x are sigma invariant. Basically, it says that the integral is well defined. And the theorem is that there exists sigma psi such that such an equality holds. Okay. So it looks a bit mysterious, the object here. But this is a Mellin transform of a solution. We call them generalized gamma functions. Gamma function would be an example, though in the classical gamma function, sigma is not a loop. So we are in a bit even better situation. We do loops such that it's really very well defined.
Actually, a little question, where does your delta go? Because you made a choice of delta.
Where does my delta go?
So
It's here, yes. But
So
I
the
have to
delta
explain
changes-
you. Okay, let me tell you just one thing about this theorem. This is a generalized gamma function, and one can define it in terms of homology of local system of solutions of L, which I will do on Thursday. We have a study group on the paper of Golyshev and Zagier and our paper, so I'm going to speak about this theorem and its proof. And the object here is canonical. It's unique up to some rescaling. We can define it very nicely, this generalized gamma function here. And the delta is here. To define it, I would use the delta. I'm not showing you the
So
construction.
it might be clearer if you added the word a certain loop.
Yeah, I know
Some.
A.
So you said exists sigma, so there is a sigma, there is a
This is
solution of
a
some.
very strong thing in English.
Right, but
Say
it's-
A.
Well, exists.
We don't get to choose the loop.
There exists. Okay. And on Thursday, if I got you interested in this, on Thursday I will be speaking about this theorem and the
So first it will be
canonical
the loop.
construction of the gamma function here, the generalized gamma function. So for now, let me say why this theorem is the first step in this problem. So for that, we would need, you see that kappas are Taylor coefficients of this thing here. So they become polynomials like rational linear combinations of the powers of 2 pi I and Taylor coefficients of such a generalized gamma function. Taylor coefficients of a generalized gamma function are, let me write it as this, as gamma of x. If I want gamma of x, j's derivative at 0, that will be an integral of log t to the power j times psi of t dt, or that thing can be written as an iterated integral of the form dt over t. So there will be j factorial, j times psi of t dt over t. Iterated integral means it's a simplex integral. Chen defined this kind of iterated integral. I will speak about it on Thursday, about how this thing is defined. But anyway, we have some explicit iterated integrals here. And then iterated integrals are, they are periods of the relative completion of the first fundamental group of P1 minus singularities of L and minus 0 there is some fundamental group of that. There is a relative completion of this group with respect to the monodromy representation. This is an affine algebraic group, and there is a series of papers of Richard Hale where he constructs the Hodge-Durham theory of this group, the relative completion. But so in down-to-earth terms, we have them as explicit iterated integrals. And if we want to prove these formulas, so we have some explicit integrals of modular forms, for example. That already shows they are periods in some naive sense of Zagier. But if we want to do this motivic construction, this is work in progress. But the hint is that we have iterated integrals, and there is a structure of iterated integrals. So that might be the relative completion of the fundamental. Okay, so please, if you are interested, come on Thursday. I will explain this theorem.
Ron, is the lecture on Thursday at the time that it's listed to be, or is it?
I think so.
What is it
will
listed?
announce it, so.
What time is that? Yeah, looking at court, no, 3 o'clock, I think.
Okay, well, I know you told me there was some change.
That's for the future.
For the future.
So it's the same, 3 to 4.
Questions for the speaker?
Out of curiosity, have you gotten some way to, like kappa 4 or kappa 5, or could you?
Work in progress.
I mean, you can write kappa 4 just kind of naively following our paper as an integral of something like either integrals of either integrals.
Yes,
but I
didn't finish.
I couldn't see how to get from that to zeta 4.
Yes, but I'm trying to do that almost. Yes, we want to get your formulas proved.
And the connection with the gamma conjectures, what I talked about last time. So last time I said that when we found this numerical, I was so positive, thought we will never know why it changes between 10 and 11. And Vasily said, no, we know exactly why it changes. It's because this really is geometry in the sense of P conforms. But very nearly, I believe, with these sections. The formulas up to j equals 10, but no longer for j equals 11. Can you see that in this language? I mean, it's quite different.
No.
So you don't see here a difference between 10 and 11 in
very
this case.
peculiar about this situation, this 11, I believe. And,
No, but here exactly. I mean, the reason is because this follow is a section of a section of a section of something 10-dimensional, but that's not a section of something 11-dimensional. But I'm just wondering if in this language, from this other interpretation, in the Apéry case, do you see any difference between 10 and 11 yet?
No, not yet.
Okay. So,
but I want to see it though, so that's why we continue to work on your conjecture.
Don, if we took another one of the 17 cases, I mean, presumably that wouldn't be true.
well, we took one other, and we again got multiple zeta values after a bit.
Yeah, but a bit wouldn't be 11.
Oh no, the 11 we know why it's 11, because that particular variety, V12,
Yeah.
is a
that's what I'm saying.
three-dimensional variety, which is a
So
seven.
this kind of confirms that idea. If you took a different one of the list.
Yeah, but here, if you fix one, like the Apéry one, you get this gamma function. You can see, as you said, that they're all periods of some sort. But can you see why kappa 10 is a simpler kind of a period than kappa 11? It's a harder kind of a period. They're both periods.
This question is so interesting that if we find out, I believe we will do the answer to this problem, right? Though it's a particular case, but to explain why kappa 11 involves the multiple zeta value and up to 10 we only have zeta products, that's some structure we can see yet. Thank you.
This should be fantastic lectures. Very slow and